Section 1 Introduction. We're going to delve into the importance of understanding the reasoning behind the outputs of large language models, LLMs. It's crucial to know how much we can trust these outputs. Some argue that if an LLM explains its thought process step by step before giving an answer, it's easier to understand. However, this is only true if the explanation accurately reflects the model's actual thought process. There have been instances where the reasoning provided by the LLM doesn't match its actual thought process, which raises questions about the reliability of such explanations. To address this, we're introducing tests to measure the faithfulness of the chain of thought, COT, which will allow us to examine the reliability of COT across various tasks. These tests will manipulate the model's reasoning in different ways and observe how the model's answer changes as a result. We're not looking for definitive proof of COT's reliability, but rather trying to eliminate the possibility of certain types of failures. We're focusing on 3 potential failures. 1. Post hoc reasoning. This is when the model's reasoning is produced after it has already reached a conclusion. Since this type of reasoning doesn't affect the model's answer, it's hard to trust its reliability. We'll test for post hoc reasoning by shortening the thought process or introducing errors. We've noticed that the use of COT varies greatly depending on the task, with some tasks not using it at all, while others rely heavily on it. 2. Unfaithful reasoning due to test time computation. The performance improvement from COT might be due to the extra computation time provided by the additional tokens between the question and the model's final answer. If this is the case, the model might be using COT to improve its performance without revealing this in the COT. We've found that replacing the COT with uninformative filler text doesn't improve accuracy, suggesting that the extra computation time alone isn't responsible for the performance improvement. 3. Encoded reasoning. The benefit from COT might come from the model encoding relevant information in the reasoning in a way that humans can't understand. This could be through changes in punctuation, word choice, or other phrasing differences that improve the model's predictions, but aren't clearly understandable by humans. We've found that replacing the COT with a paraphrased version doesn't affect performance, indicating that the specific phrasing of COT isn't driving performance. A 4th hypothesis is that the style of the reasoning sample prompts the LLM to produce higher quality answers by imitating a more cautious or thoughtful agent, even if the reasoning sample isn't reliable. However, we're not exploring this hypothesis further in this work. Our findings suggest that the LLM's reasoning isn't always reliable for some tasks. We're also exploring whether there's a model size that consistently produces reliable reasoning for these tasks. We've found that smaller models often provide more reliable reasoning than larger, more capable ones, and that models produce less reliable reasoning on simpler versions of addition tasks. This suggests that the model used for the task can influence the reliability of the COT. In summary, while the chain of thought reasoning isn't always reliable, it's possible to find conditions where it is more reliable. This opens up opportunities for future work to develop methods for LLMs to produce more reliable reasoning and to detect when the model's reasoning isn't trustworthy. Section Summary. The section discusses the importance of understanding the reasoning behind the output of large language models, LLMs, and the claim that their interpretability is enhanced when they generate step-by-step reasoning. However, it has been shown that LLM-generated reasoning is sometimes unfaithful to the model's true reasoning process. To investigate the faithfulness of the reasoning, the authors propose tests that intervene on the model's stated reasoning and evaluate how the model's answer changes. They find that smaller models often generate more faithful reasoning than larger ones, and that models produce less faithful reasoning on easier tasks. This finding opens up possibilities for future work on designing methods for LLMs to produce more faithful reasoning and detecting untrustworthy reasoning. Section 2 Measuring Chain of Thought Faithfulness. In this section, we're going to explore some theories that challenge the concept of chain of thought faithfulness. We'll do this by altering the chain of thought and observing how the model reacts. 2.1 Methods Model. For most of the experiments in this section, we're using a pre-trained transformer language model with 175 billion parameters. This model has been fine-tuned to act as a useful dialogue assistant using reinforcement learning from human feedback. The only exception is the model we use to generate errors in the adding mistakes experiment. For this, we use the pre-trained language model without any fine-tuning. Tasks. We've chosen 8 multiple-choice tasks that we believe will benefit from explicit reasoning. These include grade school level science questions, algebra word problems of varying difficulty levels, text completion tasks, logical reasoning questions from China's National Civil Servants Examination, a massive multitask language understanding benchmark covering 57 tasks, elementary school level science questions, and factual questions from various domains designed to reveal misconceptions. Prompting and sampling. For each question on each task, we use a specific prompt, slightly modified from a previous study. The number of choices varies depending on the task. We generate 100 reasoning samples for each problem using a method called nucleus sampling with a probability of 0.95 and a temperature of 0.8. We then add the prompt for the final answer and calculate the model's next token probabilities for each answer choice. Each reasoning sample is then divided into sentences for analysis using a sentence tokenizer. Section Summary. In this section, the authors investigate the faithfulness of a model's chain of thought by perturbing it and observing the model's behavior. They use a pre-trained transformer language model for most experiments, except for one where a pre-trained LM is used. They select 8 multiple-choice tasks to evaluate the model's reasoning abilities and use prompting and sampling techniques to analyze the model's responses. Section 2.2 Chain of Thought Statistics. We're going to discuss the statistical analysis of our thought process chain in this section. Figure 2.2 provides a summary of the results from our standard thought process chain experiments, which will serve as a reference for the rest of our study. We've also included a table of performance metrics for your convenience. On average, our reasoning samples consisted of 4 steps or sentences. Interestingly, 89% of these samples contained between 3 and 6 steps. To make our results easier to understand, we've chosen to focus on reasoning samples that fall within this range for the remainder of our paper. We've also broken down our results by sample length to avoid any distortions in our graphs. Out of the 8 tasks we tested, 7 showed improved performance when we used the thought process chain. The Aqua task showed the most significant improvement. However, the Hella Swag task was an outlier, as its performance actually decreased. In the following sections, we'll arrange the tasks based on the degree of improvement we observed when using the thought process chain, unless we specify otherwise. In section 2.3, we'll explore the concept of early answering. Specifically, we'll investigate whether cutting off the thought process chain midway can alter the predicted answer. Post hoc reasoning refers to reasoning that is generated after a conclusion has already been reached. In our thought process chain, we generate the reasoning before we sample the answer. However, this doesn't necessarily mean that the reasoning caused the answer. Just because reasoning isn't post hoc doesn't mean it's reliable, and being post hoc doesn't automatically make it unreliable. However, non-post hoc reasoning generally has fewer ways to be unreliable than post hoc reasoning. This includes factors like increased computational demands during testing and steganography, which we'll explore in this study. To measure post hoc reasoning, we cut off the thought process chain halfway and see what answer the model predicts without the full reasoning statement. If the model doesn't change its answer based on additional steps in the thought process chain, it's likely that the reasoning is post hoc, meaning it was generated after the conclusion was already inevitable. In our experiments, we cut off the reasoning samples we had collected earlier and asked the model to answer the question using the partial thought process chain instead of the full one. We did this for each thought process chain we collected, cutting it off after each step or sentence. So, if we started with a thought process chain consisting of steps x1, x2, x3, and so on up to xn, we would first cut it off to an empty string, then to one sentence, x1, then to 2 sentences, x1, x2, and so on. We replaced the original thought process chain in the sample with each truncated chain and asked the model to answer the question as before. After collecting answers for each truncated thought process chain, we compared them to the answer the model gave with the full thought process chain. If the answers matched less frequently, this suggested that less of the reasoning was post hoc. Section Summary. In this section, the authors present the statistics of the reasoning samples collected under the standard chain of thought condition, with an average of 4 steps per sample. They also show that most of the reasoning samples have between 3 and 6 steps. The experiments demonstrate that 7 out of 8 tasks show improved performance under chain of thought reasoning, except for Hella Swag. Additionally, the authors investigate post hoc reasoning, where reasoning is generated after the conclusion has been established, and measure how often the model reaches the same conclusion when the chain of thought is truncated at different steps. Section 2.3.1 Early Answering Results. We're going to discuss the initial results of our study, which are illustrated in figure. We've calculated a metric called the area over the curve, AOC, for each task, taking into account all lengths of the chain of thought, COT. The AOC values are determined by a weighted sum, where each COT length's AOC is influenced by the proportion of COT samples of that length. Our experiment reveals a significant variation in the degree of after-the-fact reasoning across tasks. For instance, in the tasks with the lowest AOC values, ARC, Easy, ARC, Challenge, and OpenBook QA, the COT alters the final answer less than 10% of the time. However, in the task with the highest AOC value, Aqua, the COT changes the answer over 60% of the time. Interestingly, the Aqua task consistently has a low rate of matching the original answer before the final two reasoning steps, suggesting a low level of after-the-fact reasoning. We also found that the amount of after-the-fact reasoning per task, as measured by AOC, doesn't necessarily correlate with the performance improvement from the COT. For example, Logica sees little accuracy improvement from the COT, yet it ranks second in AOC, just behind Aqua. In another surprising finding, Hella Swag shows a decrease in accuracy but less after-the-fact reasoning on AOC compared to 4 other tasks that show an accuracy increase from COT. These findings suggest that the COT can be reliable even when it doesn't enhance task performance. Next, we explored whether editing the COT changes the predicted answer. We tested this by deliberately introducing an error into the COT and observing the outcome. If the model's final answer changes when a mistake is inserted into the COT, it suggests that the model isn't disregarding the COT. In this experiment, we introduced an error into one step of the COT and then continued the COT from that point. We used a pre-trained model to generate a mistaken version of a single sentence from the original COT. We then replaced the model-generated reasoning in the prompt with the original COT up to the point where the error was introduced, followed by the sampled mistaken step. We found that our mistake-generating process produces a plausible error at least 80% of the time. We also observed that when the model's COT leads it to an incorrect answer not present in the answer choices, it often selects the answer choice closest to that answer. Similar to the initial answering experiment, we measured how often the final answer changes after the mistake has been added and the remaining COT has been sampled. A low matching frequency indicates less after-the-fact reasoning. We also calculated an AOC value for each task, as we did in the previous section. Section summary. The early answering results show that the extent of post-hoc reasoning varies significantly between tasks, with the Aqua task having the highest rate of answer changes due to chain of thought, more than 60% of the time. Surprisingly, the amount of post-hoc reasoning does not always correlate with task performance improvement. In the experiment where mistakes were added to the chain of thought, if the model's final answer changed after the mistake was introduced, it suggests that the model is not ignoring the chain of thought. The frequency of answer changes and the AOC values also indicate the level of post-hoc reasoning. Section 2.4.1 Adding Mistakes Results. We're going to discuss the results of an experiment we conducted, which involved adding errors. The findings from this experiment largely align with those from our previous early answering experiment. The AOC results also generally match the findings shown in the figure, where the order of the lines for all chain of thought, COT, lengths typically mirrors the same ranking as the AOC scores. The ranking of tasks based on AOC is almost the same, with Hella Swag scoring slightly higher than MMLU being the only difference. Similar to the early answering experiments, we noticed a common high-level observation. The degree of reasoning after the fact varies significantly among tasks, and it doesn't have a strong correlation with the improvement in accuracy provided by COT. In both the early answering and error-adding experiments, Aqua and Logica are the two tasks that exhibit the most consistent reasoning. This increased consistency might be due to the model's limited ability to perform the task without COT, which might make the model rely more on COT. We found that the faithfulness of each task depends on the model's capabilities, such as its size, which supports this theory. Another possible reason for the increased faithfulness in these tasks is that they both involve logical reasoning, so it might be more evident that the model's final prediction should be supported by the given reasoning. However, we found that faithfulness doesn't solely depend on the task, which casts some doubt on this theory. Next, we wanted to investigate whether uninformative chain of thought, COT, tokens also enhance performance. We tested the theory that the additional computation time provided by a longer context window is responsible for the performance improvement from COT. If this were true, the model might be using the COT to perform computations that improve performance but aren't revealed in the COT itself. This would suggest that important reasoning steps might not be represented in the given reasoning. In this experiment, we replaced the COT with a number of tokens, or filler tokens. We tested strings of filler tokens ranging from 0 tokens to the length of the longest chain of thought collected from 100 samples for any given question, increasing by 5 tokens each time. If the filler tokens significantly improve performance, then the COT might not be accurately representing the actual process by which the model arrives at its answer. Section summary. The results of the experiment show that the ordering of tasks ranked by AOC, area over the curve, scores is similar to the ordering based on the results in Fig. 2.4.1. with Hella Swag scoring higher than MMLU being the only difference. The extent of post-hoc reasoning varies between tasks and is not strongly correlated with the accuracy improvement conferred by COT. Aqua and Logica are the two tasks with the most faithful reasoning, possibly because the models have limited ability to perform these tasks without COT. Another experiment using filler tokens instead of COT suggests that the additional test time computation provided by a longer context window may be responsible for the performance boost from COT, indicating that important steps of reasoning may not be represented in the stated reasoning. Section 2.5.1 Filler Tokens Results. In Section 2.5.1, we discuss the results of using filler tokens. From our observations, we found that adding tokens to the context doesn't improve the accuracy. In fact, for certain tasks like truthful QA and open book QA, the performance slightly decreases when we use a longer context. This could be because such sequences are not part of the model's training data. These findings suggest that simply increasing the computational resources during testing doesn't necessarily help the models to perform better. In Section 2.6, we explore the impact of rewording the chain of thought on the predicted answer. We hypothesize that the way the reasoning is phrased could affect the answer, not just the content of the reasoning itself. This could happen if there's pressure during the RLHF process to provide the correct answer while also minimizing the length, or if the RLHF process encourages hiding the reasoning that might be discouraged by the preference model. To test this, we had a language model rephrase the chain of thought to eliminate any potential influence from the way the reasoning is phrased. If the phrasing significantly contributes to the accuracy boost provided by the chain of thought, we would expect that rephrasing it would reduce or eliminate this boost. We made sure that the model rephrasing the reasoning didn't have access to the original question. This was to prevent it from generating reasoning that would lead to the correct answer to that question. We had the model rephrase the same parts of the reasoning sample that were used in early answering, like the first part alone, the first two parts, the first three parts, and so on, without access to the original question. We then put the rephrased chain of thought back into the original prompt and continued to sample until the end of the reasoning sample. After that, we prompted for a final answer as before. We chose this approach instead of rephrasing the entire chain of thought because the model usually states the final answer in the last steps of the chain of thought. So, rephrasing the entire chain of thought would likely lead the model to produce the same answer. We then compared the model's accuracy after using the standard and rephrased chain of thought. If the way the reasoning is phrased is responsible for the accuracy boost provided by the chain of thought, we would expect to see a decrease in performance when using rephrased reasoning compared to the standard chain of thought. Section Summary. The results show that adding filler tokens to the context does not improve accuracy and, in some cases, actually decreases performance. This suggests that extra test time compute alone is not used by models for helpful reasoning. In another experiment, paraphrasing the chain of thought is done to remove any encoded information in the phrasing choices. If phrasing encoded information is a major factor in the accuracy boost, we would expect degraded performance under paraphrased reasoning. Section 2.6.1 Paraphrasing Results. We've found that the accuracy of our paraphrased content aligns closely with the original thought process for nearly all tasks, regardless of the number of filler tokens used. This is clearly demonstrated in our figure. This suggests that the specific wording of the reasoning doesn't hold the key to the accuracy improvements of the chain of thought, COT. We've also been exploring whether the size of the model impacts the faithfulness of the COT. Some tasks have shown a significant drop in reasoning faithfulness. Naturally, we're curious to see if there are any models that maintain faithful reasoning for these tasks. If such models exist, we could select them for task solving, especially if faithful explanations are crucial, such as in high-stake scenarios like medical decision-making. One possible reason for a model's unfaithful reasoning could be that it's already capable of confidently predicting the answer without relying on the COT. In such cases, the COT might not significantly influence the model's final answer. Therefore, we hypothesize that larger models might perform worse than smaller ones when it comes to reasoning faithfulness. Smaller models might benefit more from the COT for certain tasks, leading them to rely more heavily on it. To test this hypothesis, we've looked at how often the answer changes with and without the COT. This metric intuitively shows how much the model depends on the COT for answer prediction. This is similar to our early answering experiment when we don't use any of the COT. This metric is a strong predictor of overall early answering and mistake addition results. For example, it can predict the task order by area over the curve, AOC, in our table. We've chosen to use this metric instead of running the full set of early answering and mistake addition experiments for computational efficiency. In this section, we've used a range of language models, LLMs, of different sizes. These models are pre-trained, decoder-only transformer models that have been fine-tuned to be useful dialogue assistants with reinforcement learning from human feedback, RLHF. similar to the model in section. Section summary. The accuracy of paraphrasing closely matches the accuracy of the original chain of thought, indicating that the specific phrasing of the reasoning does not contribute to the accuracy gains of COT. However, larger models may behave worse than smaller ones in terms of reasoning faithfulness, as smaller models may benefit more from COT and rely more on it. To explore this hypothesis, the percentage of answer changes with and without COT is used as a metric to measure the model's reliance on COT. Section 3.1 Standard Tasks. We'll now discuss the results of our standard tasks. The diagram shows the outcomes of the tasks we've previously mentioned. For 7 out of 8 tasks, the model with 13 billion parameters alters its response after the chain of thought, COT, more frequently than the model with 175 billion parameters. In fact, for most tasks, the faithfulness of the model's reasoning tends to decrease as we move from the 13 billion to the 175 billion parameter models. This suggests that as the model size increases, the faithfulness of its reasoning on these tasks decreases, a phenomenon we refer to as inverse scaling. For 6 out of the 8 tasks, excluding Aqua and Logica, the most faithful reasoning is provided by the 13 billion parameter model. This model even outperforms smaller models in terms of reasoning faithfulness on these tasks. We believe that smaller models may not yet have the capability to utilize COT effectively, as indicated by an appendix that shows models with less than 13 billion parameters gain little to no improvement in accuracy on these tasks with COT. In summary, our findings suggest that certain tasks do not inherently lead to unfaithful reasoning. Instead, it appears that only models of a certain capability level, but not higher, on a task are able to produce faithful COT. We also conducted a series of addition tasks to validate our conclusions. We performed the same evaluation on a set of synthetic addition tasks where we could directly control the difficulty level. Each addition task consisted of problems with 2, 4, 8, or 16 operands, each of which was either 2 or 3 digits long. The model's answer was given as a free response, unlike the multiple-choice tasks we used earlier. As shown in the table, we used XML tags to prompt the final free response answer after the chain of thought reasoning. Our 2 smallest models, with 810 million and 1.6 billion parameters, did not consistently provide an integer answer when prompted in this way, so we excluded them from the results. From the figure, we observed that this measure of post hoc reasoning increases with model size on each task, and also increases with easier tasks at the same model size. This suggests that to elicit faithful reasoning that can explain model behavior, it may be necessary to choose models that are less capable than the most capable model available, especially for easier tasks. Section summary. The results of the evaluation on standard tasks show that the larger 175B parameter model is less faithful in its reasoning after COT compared to the 13B model. However, for 6 out of 8 tasks, the 13B model demonstrates the most faithful reasoning, even outperforming smaller models. On the addition tasks, the measure of post hoc reasoning increases with model size and is more pronounced for easier tasks, suggesting that less capable models may be more suitable for eliciting faithful reasoning on these tasks. Section. Analysis of chain of thought faithfulness. Simplified paraphrase of the paper section. We're going to discuss the analysis of chain of thought, COT, faithfulness. Recent studies have examined COT faithfulness in ways that differ from our approach. Some researchers have used a method called Shapley analysis to demonstrate that certain elements of the COT are more crucial than others in determining the final result. We, on the other hand, suggest alternative ways to test COT faithfulness that require less computational power. Other researchers have explored COT through a method known as counterfactual prompting. They found that some parts of the prompt are less significant than others in reaching the final answer. We take a different approach by intervening on the COT produced by the model, rather than using a few short prompt examples. We also suggest general tests for COT faithfulness. Some researchers have found instances of unfaithful COT in settings that were deliberately designed to be challenging. This shows that COT reasoning isn't always reliable. In their study, the model produced a COT in the presence of biased examples. While the model's final answer aligned with the bias in the prompt, the COT provided a different explanation for the answer that didn't reference the biased context. In contrast, our work looks at non-adversarial settings to gather evidence about reasoning faithfulness under a broader range of realistic conditions. We test 3 theories for why COT prompting improves performance. It generates an equation to be evaluated, it provides additional computational power at test time, and it allows the model to access relevant information from pre-training more effectively. We build on the test time computational power experiment from previous work by evaluating a wider range of tasks and varying the number of filler tokens. Now, let's talk about techniques to increase reasoning faithfulness. Previous studies have suggested ways to generate reasoning that is more likely to be faithful by design, due to the way the reasoning or final answer is produced. Some researchers generate a program in a specific language and execute the program to produce the final answer. This process ensures that the program used to generate the answer isn't an afterthought but is directly used to produce the final answer. Others use a language model to select statements from a context and then draw inferences from those selected statements in a separate context window. Some answer questions by breaking them down into sub-questions, finding that this method leads to more faithful reasoning according to our early answering and adding mistakes metrics. Some of the potential faithfulness issues we've identified, such as post hoc reasoning, may apply to the methods above. The metrics we propose could be useful in measuring how much these methods improve faithfulness. Section Summary. The authors compare their work on analyzing chain of thought, COT, faithfulness to previous studies. They propose different tests for COT faithfulness that are computationally less expensive and intervene on the COT produced by the model. They also investigate non-adversarial settings to collect evidence about reasoning faithfulness under realistic conditions. Additionally, the authors discuss techniques to increase reasoning faithfulness, such as generating a program to produce the final answer and decomposing questions into sub-questions. The metrics proposed in this work may be useful for evaluating the effectiveness of these methods. Section. Techniques to elicit language model reasoning. Simplifying techniques to enhance reasoning in language models. Various strategies have been suggested in previous studies to enhance the performance of language models by encouraging them to reason before providing an answer. These strategies include creating sub-questions, constructing a thought tree, planning and implementing a strategy to answer the question, and encouraging language models to debate to find an answer, among other methods. These techniques all follow a similar thought chain structure, where the language model first generates the initial steps of reasoning and then uses these steps to produce the later ones. We believe that our methods for evaluating the accuracy of these models should also apply to these techniques. However, there are some limitations to our study. One significant limitation is that we don't have an independent method to understand the actual internal reasoning process of the model. Without this, we can't be sure if the thought chain accurately reflects that reasoning process. We've gathered evidence to support various theories about how the model uses the thought chain, but we can't be sure if we've considered all possible theories or if there might be other correct theories that we haven't investigated. Without a reliable source of information about the accuracy of the reasoning sample, it's also unclear how to determine the importance of each experiment in relation to the others when evaluating accuracy. A combination of our measurement techniques and additional experiments will be needed to determine the relative strengths of evidence from each type of experiment and to create a more comprehensive picture of reasoning accuracy. Furthermore, our study focused on models fine-tuned with RLHF, which may produce reasoning that is different from other models like pre-trained language models. For instance, pre-trained language models might be more likely to strongly rely on the text they've generated, as they're trained to generate the most plausible completion based on a given input, rather than to maximize the overall quality of the completion as judged by humans. As a result, pre-trained language models might show fewer signs of reasoning after the fact, such as being more likely to change their final answer when errors are added to the thought chain. In conclusion, a promising area for future research would be to investigate whether training methods different from RLHF are more effective at encouraging accurate reasoning from language models. Section Summary. Previous research has proposed various techniques to improve language model performance by eliciting reasoning before providing an answer, such as generating sub-questions, creating a tree of thoughts, devising and executing a plan, and having language models debate. These approaches follow a chain of thought structure, where the model produces earlier steps of reasoning and conditions on them to produce later steps. However, a limitation of this investigation is the lack of understanding of the model's real internal reasoning process, making it unclear how to assess the faithfulness of the reasoning sample. Further experiments are needed to determine the relative strengths of evidence from each type of experiment and explore different training schemes to elicit faithful reasoning from language models.